name's Kathy. I'm just going to talk about the inhomogeneous diffusion equation, or an example of one. So usually when we see inhomogeneous diffusion equations, the inhomogeneity is due to the boundary conditions, but I think this example was either on a practice midterm or homework or something like that, and the inhomogeneity was actually in the equation itself. And I found that to be a little confusing, so I thought I would just walk through it and kind of break it down a little bit more. So let's get started. So here is the equation itself. Partial derivative with respect to t is equal to the double partial derivative with respect to x minus 1. So it's that minus 1 at the end that makes this kind of tricky. The boundary conditions are listed below along with the initial condition. So we know that the solution looks something like this. There's going to be a steady state, and also I'm going to call it a particular solution because I'm not sure how to pronounce it. But yeah, this kind of looks analogous to when we did ordinary differential equations that were inhomogeneous. So first we're going to look at the steady state solution, and the steady state solution, which I'm going to refer to as u sub s of x, is also a solution to the original equation, which means that we can write what I have written below. It actually solves the equation itself. So since the steady state solution is only in terms of x, the partial derivative of it with respect to t is going to be 0. So what that means is 0 is equal to the double partial derivative of u sub s of x minus 1. So since that's equal to 0, you can just move the 1 to the other side, take the double integral, and you get the steady state solution to be 1/2 x squared plus bx plus c. Then what we're going to do from there is plug in the boundary conditions. So here I am doing that, the first one being that the partial derivative with respect to x is equal to 0. So plugging that in, you find that the constant b is equal to 0, which means that you can write a slightly simpler form of the steady state solution to be u sub s equals 1/2 x squared plus c. And then to solve for c, we plug in the second boundary condition, which is that the equation evaluated at 5 is equal to 0. So that would mean that c is equal to negative 25 over 2, and that gives us our form for the steady state solution being 1/2 x squared minus 25 over 2. Now for the particular solution, we're going to use our strategy of separation of variables, which means basically that we're going to guess that the solution is something in terms of x times something in terms of t. And the reason why we can't just start doing this from the beginning is that we had that minus 1, so if we tried to just use separation of variables and plug in our ansatz into that equation, it would get messy because on the other side you would have that minus 1 to deal with. But when we split it up this way, we can use that ansatz once we've already solved for a steady state solution. And that's because the steady state solution accounts for the inhomogeneity, and that means that u sub d is now going to solve the homogeneous diffusion equation that we're all familiar with and that I have written below. So here I am just plugging in our ansatz into the diffusion equation and solving for x and t, which I have listed below, and this is very familiar. This is something that we have at this point probably done a lot. So yeah, here I am just solving the ordinary differential equations. One of them is in terms of t, the other one is in terms of x. So here we have our form for u sub d. Looks a little bit messy. It's e to the negative k squared t times a sine kx plus b cosine kx. Now what is convenient is that our boundary conditions are also homogeneous, and I gave an example of one of them below, which is that u of x sub t, or u of x and t is equal to u sub s plus u sub d. And one of the boundary conditions is that u of x equals 5, comma t is equal to 0. And if you'll see, when you plug that into the full equation for u of x and t, you find that u of 5, comma t and u sub s of 5 are both equal to 0, which leaves you with u sub d evaluated at 5, comma t is also equal to 0. And this also holds for the other boundary condition. I didn't write it out, but if you were to write it out, you would see that that holds. So now basically we're plugging in the boundary conditions, which as I previously mentioned are now homogeneous, and we're solving for what we need to solve for u sub d. So first we find that k sub n is equal to n plus 1/2 times pi over 5. And here I am plugging into the second boundary condition where I find that the constant a is equal to 0, or the coefficient a is equal to 0. So here we have a more simplified form of u sub d, which is e to the negative k squared t times b cosine kx. Now we're going to apply the idea of Fourier series. So we're basically summing up over all the coefficients. So u sub d is equal to the sum of b sub n cosine kx times e to the power negative k sub n squared t, where, as previously said, k sub n is equal to n plus 1/2 times pi over 5. And now, finally, for the initial condition, which is that u of x comma t equals 0 is equal to x squared times 25 minus x squared. So basically, we're just going to write out our full equation, which is the second line here, where we put in the steady state and u sub d. And write that out. It looks a little messy, but we plug in t equals 0, and then we're going to solve for the coefficients b sub n by applying the idea of Fourier series in the next slide. So here we are solving for b sub n. It's just the inner product of the initial condition minus the steady state, which is x squared 25 minus x squared minus 1/2 x squared minus 25 over 2. The inner product of that with cosine k sub n x divided by the inner product of cosine k sub n x and cosine k sub n x. And yeah, from there we can write out our full solution basically, which is on this slide. It is still the second line here, but you're going to replace the b sub n with the equations on the slide we just saw, and the k sub n with the equations we saw before as well. So here's like basically the final form of the solution, and then you would also write that b sub n, the b sub n's would be equal to this, and the k sub n's would be equal to that. So it's really not that much more complicated than a normal diffusion equation, but it can get just a little messy with writing a lot of things out. So it's important to just kind of sort through it and break all the steps down. So hopefully this was helpful. Yeah, thanks for watching. Bye.